Hello and welcome. In this video series, we're going to take a look at the indefinite integral and iterated integrals, which will be new to the concept of multivariable calculus. But before we get into that, let's do a Calculus 2 reboot and think about what an integral is and how an integral works. So here we have a graph, and this graph shows the speed of a car over the course of 4 hours. So the red line indicates that the car is traveling at a constant speed of 50 miles per hour over the course of all 4 hours. So notice that we have speed along our vertical axis and we have time along our horizontal axis. So there's speed and there is time. And so because we know that if a car travels at 50 miles per hour, 50 miles per 1 hour, but we repeat that over the course of 4 hours, well, that's going to be 50 miles plus 50 miles plus 50 miles plus 50 miles. And so if we multiply this by 4 hours, we also get a beautiful dimensional analysis, and we see that that comes out to a total of 200 miles. Now, the significance of this that we learned in calculus is that what we've just found, this product, happens to be the area of the rectangle that starts over here at 0. I lost my cursor. There it is. So over here, if we make a rectangle out of these corners here, we see that the area of that region of all of this right here is going to be the height of that rectangle, which is the 50 miles per 1 hour. And then the horizontal, the length of it is and its units are hours, and so we see that what we've really computed is the area of this gigantic rectangle. And that works again because of the dimensional analysis that we have conducted. But we also should be cautious of this approach because we know that not all graphs result in a function that is perfectly clean and has a formula for the geometric area of it. So in this case, we see that the car starts going 50 miles an hour, but if we looked at this every fifth of an hour, then we see that the speed is progressively getting lower and lower until eventually at time, I guess this is 1 in this case, at time 1, the car has come to a complete halt. So this car is progressively slowing down over the course of that period much and much faster. And so to find the area of it, we could try to think about this as one big rectangle, but notice that if we treated this as our rectangle, then we would end up computing an overestimate of the overall distance because we'd be assuming that the car was going at 50 miles an hour over the course of that entire 1 hour. So maybe what we've historically done is we've thought about this as, well, we could create rectangles in here, and there's one. And then I can create another one by looking at the speed at time 0.2 and saying, well, I'm going to pretend that that's constant over the course of that 0.2 hour period. Of course, this here is distance that did not get covered, but that we're going to compute in that area anyway. And so this is one of still the challenges that we faced in Calculus 2 is how do we avoid that error? And one way in which we could do that is to use more rectangles that have a smaller width. And then if we broke this in half and only assumed up until this point, and then use the speed at that point to indicate the height of the next rectangle, we'd be better off. But, of course, this is an expensive process if you're going to be doing it by hand. So if we just broke it up into these reasonably sized rectangles whose areas we could pretty quickly calculate, let's go ahead and do that. So we see that this first rectangle here has a height of 50 miles an hour. So this is 50 miles an hour. I'll just indicate this with a 1. So its area is 50 miles per 1 hour multiplied by 0.2 hours. That's the width of our rectangle down here. And so when we multiply those together, we get a total of 10 miles. And now we do the same thing for the next rectangle. And of course, we're going to accumulate these because we want to add up all the distances. We don't just want the distance over the first 1/5 of an hour, we want it over the course of that full hour. So we approximate that, maybe about, let's see, 2, 4, 6, 8, about 48 miles an hour seems reasonable as an estimate to eyeball this. And multiply it again by 0.2 hours, because that's the duration of time over which we're assuming that constant speed. And that's going to come out to 9.6 miles. And that's region 2. So region 3, similar process, except here we see the car has slowed down to about 42 miles. So we'll just say 42 miles per hour rather. So 42 miles per hour multiplied by 0.2 hours will give us, let's see, that'll be 8.4 miles. And we do this 2 more times, once for this guy, height of, I'm going to say that's about 33 miles an hour. So in the 4th region, we're going 33 miles an hour. We're doing that for 0.2 hours, which is going to come out to 6.6 miles. And we do this 1 more time. We're going to do this for the 5th region. And here's our region 5. So our 5th region looks like about 18 miles per hour. Multiplied by 0.2 hours, which comes out to 3.6 miles. Now, these are all of our individual distances. We want the sum of these because we want to know what's the estimate for the total distance over that time period. And that comes out to 38.2 miles. So that's our estimate. Now, we know that this is an overestimate, and we know that because of the fact that we're calculating in here distance that wasn't actually driven, so this extra distance here is being calculated in there. And of course, at this point, we could say, well, let's break this region up into smaller widths and repeat this process with those smaller widths, and we're going to get something that becomes more and more accurate. So we just estimated that our answer is about 38.2 miles in total. So 38.2 miles. And in our approximation above, we could always improve our estimate of the area under the curve by allowing the width of each rectangle, delta x, to get smaller and smaller. That is, we look at the limit of the area as delta x approaches 0. We write it like this. So this is the Riemann sum, and it basically says add up over all the delta x's the height times the width, and really this is just the area of that rectangle, and then this symbol means add up. But what are we doing here? Here we're saying we want to add up these areas with rectangles that have widths that approach 0. So we could read this as add up all of the length times widths, or the height times widths, where the widths are infinitesimally small. And so just to spend a minute working with this summation before we get into the official definition, or rather the official way we compute integrals, which is by calculating the antiderivative. And before we do that, let's think about how these summations work. So this thing down here is an index. So if I think about this as the sum from, let's see, how are we going to do this? We're going to say from I equals 0 to I equals, we had a total of 5 rectangles, so we'll start it at I equals 0. That integral is going to end, or that summation is going to end at I equals 4, and I'll show you exactly what that means in just one moment. And then what did we do? Well, we computed the product of the height, and I'm going to write this not as f of x, but f of xi, multiplied by the delta x, which is constant in this case, so there's no need to subscript that because all of the delta x's are the same. So what do I mean by xi? Well, if I look back at that curve, the xi were just the different x values that I had pinpointed. So where I computed the height was, we'll call that x0. And then x1 was where I computed the next height, and then x2, and then x3, and then finally over here at x4. Now, this doesn't mean time 0, time 1, time 2, time 3, time 4. This just means the next value of x. So x1 is actually the second value of x. And we said that f of x naught is equal to 50 miles per hour. F of x1, well, that was x, if we think about x naught as 0. F of x1, I think we calculated to be, let's go back here a second. We said that that second height was 48, 42. So 48, and f of x2 was, oh, I just had it, 42, is it 42? 42, 33, 18. And this was our f of x3, and this was our f of x4. Okay, so x1 was actually, the value of x1 was 0.2, the value of x2 is 0.4, the value of x3, 0.6, and the value of x4 was 0.8. And so we calculated all of these. We said, okay, this means add up. So what does this equal? Well, it means take f of x0, multiply it by delta x, which is constant. That's going to be our 0.2. This is equal to 0.2 right here. And then we repeated this for the remaining xi's. So f of x1 times delta x plus all the way up to f of x4 multiplied by delta x. And this is our computation from from number 1 up top, number 2, and then this was all the way the fifth rectangle that we computed the area of. And we said that this came out to 38.2. So this is how a summation works. A summation is important because whenever we try to say, well, how do we do this? What does this mean to add up infinitesimally narrow rectangles? They're the areas of these infinitesimally small rectangles. Then this means that we want to sum all of the height times lengths, the area of rectangles, over all the delta x increments over our interval. As the interval width approaches 0, we call delta x by the name dx, and this computation is called the indefinite integral. So you can see the relationship between what we have up here, what we have here, and what we have here is exactly the same thing. That is, add up, right? This means add up across all of the delta x's, the product of height times width, where the width is infinitesimally small. So the notation we use to write that is, well, we need to know our starting x, we need to know our ending x, and then notice that this is still f of x, that's still the height, but dx is what we're calling an infinitesimally narrow width. So if I translated this, this is still add up, right? That still means add up, but what are we adding up? Well, we're adding up infinitesimally narrow rectangles. We're adding up the areas of infinitesimally narrow rectangles. And so this still is height, and this still is width, and it means exactly the same thing. So from a mathematical perspective, we want to know, well, how does one compute this thing? And the short answer is we use the antiderivative. So this is called I'm sorry, I said indefinite integral. This is the definite integral. A definite integral is one where you end up with a number instead of a function. So the definite integral is going to be from the boundaries a to b. Now, from calculus, we learned a way to do this, and without getting into the details of the fundamental theorem of calculus, it basically said that the way to compute an integral is by taking the antiderivative of f of x. Now, integral and antiderivative sound like they might be the same thing, and they're related. An integral is a way to accumulate, but the antiderivative is the process that we go through to accumulate it. So we call the antiderivative capital F of x typically, then evaluate it at x equals b and x equals a. So this tells us, how do you do it? So let's go ahead and do it for our function up above. Suppose that I actually now gave you the function that graph was displaying, and that function is f of x equals 50 minus 50x squared. where f of x is the speed of the car in miles per hour after x hours. Calculate the exact total distance traveled by computing the integral. And so to do that, we are going to use our standard integral function, so the integral, and now we want x to go from 0 to 1 because those were our hours, so 0 hours to 1 hour. Our f of x in this case that's just a function that's going to give us the height of the curve at any given point. And again, think about this right here as height. The units of this height are miles per hour. And we're going to multiply that by infinitesimally narrow dx's. So think about this as delta x that's really, really narrow. And so this is still a width. And its units are in hours, and we're multiplying them together. So notice that what this is going to do is it's going to give us total miles. So we know how to compute the antiderivative. The antiderivative of 50 is 50x. The antiderivative of 50x squared is 50 over 3x cubed. And now we can plug in or evaluate at our endpoints. And the way we typically write that is x equals 0, x equals 1. So this is our capital F of x. This is capital F of x, what we've calculated now. It says that now we need to evaluate capital F of x at 1, evaluate capital F of x at 0, and then take the difference between those. So here we go, 50 times 1 minus 50 thirds times 1 cubed. So that's our evaluation at x equals 1. At x equals 0, we're going to repeat the same thing. As you might notice, this is going to come out to 0, the second term here. And this comes out to 33.3 repeating, so we'll just say about 33.33. And the units are miles, and we know that because we did the dimensional analysis here. So first of all, notice that this number is smaller than the overestimate that we computed, which makes sense because if we computed the overestimate, then the exact distance traveled is going to be smaller than the overestimate, and that comes out to 33.33 total miles. Great, so now we know how to calculate total area. One thing that we should point out here, or to give a little bit of intuition of why we take the antiderivative, well, if the derivative of a function is speed, then its antiderivative function is distance. And you can think about this right here as distance at x equals 1 hour, right? That's where the car is in terms of its distance at 1 hour. This is the distance at 0 hours. And it doesn't always have to be the case that you start at a distance of 0 miles. This could have been 25. But if at time 1 we were at 50 miles, and we started off at 25 miles, then that means we had driven 25 more miles. And so that explains the difference between where we are at time 1 and where we are at time 0. So now we're going to push along to iterated integrals in 3 dimensions, and I think this is a great point to stop the video, and we'll come back in the next segment to address how we would do iterated integrals in 3 dimensions.